In this video, I will go over some of the principal components of geodesy or geodesy. I have heard that pronounced both ways. So geodesy is the science of the measurement of the Earth's shape, orientation, position, and gravity. When you think about how the Earth looks from space, an image similar to this probably comes to your mind. We have been taught that the Earth was a sphere since elementary school. Well, guess what? We were lied to. And because the Earth is not a perfect sphere, we have to figure out ways to model the shape of the Earth to make more accurate measurements. I'm now going to share a short video with you about the history of geodesy that was created by NASA.
A long time ago, in ancient Egypt, a clever human named Eratosthenes figured out that when the sun was directly above a deep well in one city, you could stand in a nearby city to the north, measure the angle of the shadows there, and multiply that by the distance between the two cities to get the distance around the entire Earth. With that, the science of geodesy was born. Geodesy deals with the measurement and representation of the Earth, or to put it more simply, it's the science of where things are, and just as importantly, where they have been and where they are going. Through geodesy, we learn the rough size and shape of the Earth, the direction of its rotation, its distance from the Sun, and more. Through triangulation, we could create detailed maps of entire countries. We even figured out that the Earth isn't quite a perfect sphere, and after some arguments and expeditions to Lapland and Peru, we measured that it's just a bit thicker in the middle. Building on this information, we found tons of practical uses for geodesy. Using stars as reference points and accurate watches, we could reliably determine latitude and longitude so that ships could cross giant oceans to get where they needed to go. Explorers visited uncharted regions, mapped them, and even found the tallest mountain in the world. Later, engineers built railroads to get us to all of these places. With a little math and the same reference surface, rail tunnels could be started on both sides of a mountain and somehow still meet in the middle. Life was good. And once we invented radio telescopes and satellites, things got even better. When scientists used a bunch of small radio dishes like one big one to look at quasars, somebody got the idea that you could use these measurements to determine very accurately the distance between the telescopes. Now we can look at the movement of the Earth's crust, changes in how long days are, and how the Earth wobbles on its axis. Satellites also became very important. By analyzing their orbits, we can learn about our planet's changing size and shape and gravity, and by making laser measurements, we can look at everything from changes in the height and shape of the oceans and ice sheets to how the tides work. So, from ancient Egypt to the hundreds of satellites in orbit today, geodesy continues to have a huge impact on our lives. And all because somebody, a long time ago, decided to look down a well.
All right. Getting back to the presentation. Okay, so the link for that video is available on the slide if you would like to watch it again, or if there was some technical error where you couldn't hear what was happening. So there are two branches of geodesy, geometric and physical. They both work together to make accurate measurements of 3D objects. Geometric geodesy measures the Earth's shape, orientation, and position to accurately locate and place objects with geodetic datums and coordinate systems. I will get a bit further into that in a moment. Physical geodesy uses a geoid to measure the Earth's gravitational field, and for our purposes, to better measure height and depth. In the mid to late 1600s, Sir Isaac Newton believed that the Earth was flatter at the North and South poles and wider at the equator. He correctly thought that it was caused by centrifugal force by the Earth that it experiences when it rotates. So the Earth isn't a spheroid, but it really isn't an ellipsoid either. The Earth really just looks like a big fancy rock floating in outer space that has seen better days. Not to mention the variations up close that we experience, like the Grand Canyon in the picture on the slide, or the Alps. Here are my lovely drawings of my interpretations of the Earth's surface. Don't be jealous, please contain yourselves. The different shapes are displayed from the most generalized, and therefore the most inaccurate model on the left, the actual surface of the Earth on the right. Because the Earth is not perfectly round, we need to make mathematical estimates to measure the surface of the Earth. And because the Earth's surface varies so much and there are so many different algorithms available, the algorithm that you decide to use can create a much different result than if you would choose another algorithm. Spheroids are 3D mathematical models of the shape of the Earth based on the equation of a sphere, as are ellipsoids, but ellipsoids have a longer axis in the center, which is often associated with the equator. The terms spheroid and ellipsoid are often used interchangeably. It's the same concept as circles and ovals and squares and rectangles. All circles are ovals, also known as ellipses, and all squares are rectangles, but not the other way around. Geoids are generalized approximations of the equipotential surface of the Earth's gravitational field, very similar to mean sea level. It's what allows us to make accurate measurements of elevation. This is because gravity is not the same everywhere. I know, another thing we were lied about. As it turns out, gravity is completely location-based. Because gravity is proportional to mass, places with more mass have a stronger gravitational pull. So if you were standing on the top of Mount Everest, there would be a higher amount of gravitational pull on you than if you were standing somewhere like in New Orleans, which is about 1 meter above sea level on average, with some areas located even below sea level. We also know that not all objects have the same mass. Some material that makes up the Earth is heavier than others, and that material is not evenly distributed. Therefore, the materials that the Earth is made of can increase or decrease the amount of gravitational pull in that area, as well as the total amount of material. In terms of modeling, the geoid is like the middle ground between the surface of the Earth and the ellipsoid. It's much closer to the surface of the Earth, but still more generalized. Like with last week's lecture, generalization or simplification smooths out a surface. This is the most similar simplification by removing vertices, but instead of removing the vertices, they were just never there to begin with. That's because if we had an actual model of the Earth with all its possible potential different vertices, we wouldn't need a geoid to help us determine the location and heights. Here is a nice video created by the European Space Agency on how they created a geoid. If it will let me exit.
Geodesy was launched in March 2009 and was positioned in a very low orbit only 250 kilometers above the Earth's surface. From that orbit, Geodesy measures our planet's gravity field with a precision never obtained before. At school, we learned that the Earth's gravity is 9.8 meters per square second. But in reality, this is not entirely true. The gravity field does show differences. Geodesy feels these small differences in two ways. In the first place, the satellite is tracked by GPS satellites, and every small change in its orbit caused by gravity is recorded. Secondly, Geodesy has unique specialized equipment on board, its centerpiece being a so-called gradiometer. It measures minute changes in the gravity field, down to only 1 part per million of G. The amount of data that Geodesy has already sent to Earth is impressive.
And here we get in the order of 6 to 8 measurements per second, which means that we have several hundred millions of observations which have to be then processed to get finally a model of the global gravity field and many derived products.
The result of Geodesy's work is the most detailed map ever of the gravity field. In the Antarctic, for example, the red zones show that Earth's gravity is stronger than in the blue zones, and that reveals a lot about what's underneath the icy surface. Interpretation of Geodesy data will also help scientists to better understand the global ocean circulation system, and that will be an important step to get better insight into climate change.
It will be possible, using Geodesy data in combination with other satellite data, to determine from space global ocean circulation. We know that the oceans is nothing but a huge heat engine determining to a large part, apart from the atmosphere, our climate. So it is very important to understand how this engine really works, and I think in this respect we will make a major step forward.
The data collected by Geodesy also teaches us a lot about what's actually inside the Earth. So we'll get a clearer view of how the surface plates behave, for example, in earthquake zones.
We will gain a rather detailed knowledge of the Earth's gravity field, so to say, a look into the Earth's interior, which will help us to better understand tectonics, how plates behave, how they bend, what anomalies there are on continents and in the oceans.
Another result of Geodesy's work will be useful for engineers worldwide. This is the new refined model of the so-called geoid. To understand this geoid, we need a bit of imagination.
If the planet would be covered completely by water, the gravity field inside, or the gravity field of Earth, would shape the sea surface like that. If we had no land masses, nothing, the sea surface would look like the geoid.
This model is widely used by all kinds of scientists. It's been calculated previously, but never with the precision that we can see now. This global sea level reference will be used worldwide as the zero level of heights. This is very important for GPS navigation and major engineering projects. So the scientific world has been really thrilled by Geodesy's work, and the great news is that there is even more to come.
We have fulfilled the specified mission, but of course the scientists are very hungry to receive even more data, because the geoid becomes also better and better the longer we measure. So we have fuel for maybe another 2 years. We plan to use all fuel as long as the satellite is healthy, but we are now glad that we have fulfilled the mission we have planned originally.
Okay. So this image shows a cross-section of the different shapes that are overlapped. You can see that the surface of the Earth is the most irregular, while the geoid flows more closely with the shape of the Earth. Because the ellipsoid follows a simplified version of the surface, it will be more accurate in some areas than others, by either being too low or too high. However, it is still much more accurate than the ellipsoid, which does not take into account the surface of the Earth directly. It also shows the spheroid in green compared to the ellipsoid in red. You can see that depending on where you are on the surface of the Earth, the spheroid or ellipsoid may be more or less accurate depending on the one you choose. Datums are mathematical models used to determine the size and shape of the Earth by creating a reference surface. Here is a short video by Noah with some cool visualizations. Last video, I promise.
Mapping and surveying professionals occasionally use the term datum. But what does it mean, and why are datums important? A datum is simply a standard reference point, set of points, or surface from which survey measurements are based. It's similar to the starting points you use when giving someone directions to your house, which usually include a point that they know, like a crossroads or a prominent building. For surveyors, that starting point is usually a nearby survey mark. When adjoining properties share these common starting points, it's easier to align them properly on a map. And when we all use a network of these marks spanning the continent, we share one national spatial reference system. For many decades, we have had two types of nationwide datums in the United States, horizontal and vertical, and they were generally separate from one another. Horizontal datums allow us to measure distances and directions across the surface of the Earth. Most horizontal datums define a zero line at the equator from which we measure north and south. There is also a zero line at the Greenwich meridian from which we measure east and west. Together, these lines provide a reference for latitude and longitude. Vertical datums are used to measure elevations and water depths. Sometimes the word height is used to refer to elevation information. Most vertical datums in North America use sea level as the basic reference plane from which we measure elevation changes. Because sea level varies along the coast for a variety of reasons, the idea of using multiple tide gauges to define the vertical datum was abandoned in 1988 in favor of using just one tide gauge. Now, thanks to the Global Positioning System, commonly known as GPS, and some other space-age techniques, we are no longer limited to separate horizontal and vertical datums. Today, we have access to geometric datums, which combine latitude, longitude, height, and time information. The height information derived from GPS is relative to something called an ellipsoidal model of the Earth, instead of to sea level. While there are challenges mixing old and new positioning information, overall, new technologies like GPS help to improve the accuracy of our current datums. The North American datum of 1983, NAD 83, is the nation's horizontal or geometric datum. It provides latitude and longitude and some height information. The North American vertical datum of 1988, NAVD 88, is the nation's vertical datum, providing elevation information relative to a reference surface defined by mean sea level. U.S. territories have separate vertical datums. Unfortunately, NAD 83 and NAVD 88 aren't the only datums you will encounter. Before the current datums were defined, many maps were created using different starting points, and even today, people continue to change datums in an effort to make them more accurate. When combining data from different users or eras, it is important to transform all information to a common datum. Let's look at some examples of when and why using a consistent datum is important. Datums are commonly referenced on federal floodplain and topographic maps. Sometimes an older vertical datum for the United States is used rather than NAVD 88. In some areas of the country, especially in the West, differences between some vertical datums can be as much as 3 to 4 feet. This is pretty significant if you're trying to figure out if your house is in a floodplain. It's really important to know which datum your heights are referenced to. For any type of work where it's important for coordinates to be consistent with each other, it is critical that the same datum is used. If you are creating floodplain maps, marking property or land boundaries, designing levees or dams, building roads, or planning for coastal inundation scenarios, you must know about and use the correct datums.
All right. Okay, so to reiterate what he said before, there are two types of datums, horizontal and vertical. Horizontal datums help form the lines of latitude and longitude to accurately calculate location, length, area, and direction. They only include X and Y coordinates. When you think about horizontal datums, imagine a horizontal line in front of you. It runs parallel with the ground. Lines of latitude and longitude form a grid, and grids have lines that run parallel to each other. That line in front of you also appears to be flat. Flat surfaces are two-dimensional, lacking the dimension of height. Horizontal datums represent measurements of the two-dimensional features of the Earth in the grid. Measurements begin or are at zero at the equator in the prime meridian. But the Earth isn't two-dimensional, and its surface varies in height and depth or elevation. The horizontal datum can't handle that kind of information, which is where the vertical datum comes into play. Vertical datums allow us to calculate the difference in elevation and include X, Y, and Z coordinates. They are created with a geoid or reference ellipsoid. The term ellipsoid, spheroid, and oblate spheroid are often used interchangeably, remember. Reference ellipsoids are the more generalized shape of the Earth that we talked about in the previous slides. They are easier to use for calculations, but they aren't as accurate as using a geoid. Datums can be local or global. Global datums are created to represent the entire Earth, while local datums are made specifically for certain areas. They are made to be local or global by moving the geoid or reference ellipsoid around to best fit it to the surface of the Earth. The closer the geoid or reference ellipsoid is to the surface of the Earth, the more accurate it is. The surface of the geoid or ellipsoid is considered to be zero or sea level and is where the measurements of height and depth begin. WGS 84 and NAD 83 are the most popularly used datums in the United States, and they were created from ellipsoids. The North American Vertical Datum of 1988, or NAV 88, is the most popularly used datum created from a geoid in the United States, but soon it's going to be replaced in 2022 with a newer, even more accurate model created from a new geoid. As the video mentioned, if data with different datums are used, they need to be transformed to use a single datum before any analysis can be done. This is particularly important when measurements of only a few feet can make a world of difference, but it isn't as important for data representing large areas or when the physical measurements don't really matter. I am not going to play this final video. It's about 9 minutes long, but I highly recommend that you watch it. It's a really cool video that talks about some of the different applications of geodesy to solve real-world problems, but I didn't want to add any more material than necessary this week. I do recommend that you watch it, but it's not required.